Okay, today I want to introduce this paper, Learning Energy-Based Models by Diffusion Recovery Likelihood. It's published in ICLR 2021. Yeah, this paper is from the group of UCLA, Nian Wu, Rich Gao, and Stanford University Yang Song, Google Brain, I don't know. Okay, a brief summary. The background is the energy-based model we know as, if you know, the energy-based models use the SGLD or Langevin dynamics sampling. It has some problem. One is that it requires k steps for every iteration. So it's very slow and yeah, if you it's very slow. Yeah, why is sim if you know that, we know it starts from some random point x0, and we go through the gradient for almost following the direction of the gradient to get some to get the example. Then so this process will takes many steps for every iteration, for every model updating. So it's very slow. It's one versus uh, k times slower. And and the second problem is that ideally the sampling, the SGLD sampling should be smooth. Should be smoothly go to some good samples and good to have good samples. But maybe in reality, it will get stuck in some local optimum. So it causes some unstable instability issue. Third one is that if after training, to when you to do the inference or to sample from the model after training, then you can increase the sampling steps, the number of steps, but it will cause the oversaturated problem. So this paper is first, I think the motivation is to use the diffusion model, the almost state-of-art generative models, diffusion model, to combine it with the energy-based model. Basically, it uses the intermediate status as the milestone. Like this one, this is a milestone, another one, and another one, and the final one. So use those intermediate status as milestones, then use the SGLD to learn to denoise between the status. For example, we from this time to denoise, use SGLD to another time step or to another status. So this is the motivation and the method. Then or in the paper they further to use their strong mathematical skills to uh, create to conduct the modeling in the statistic. Yeah, they think it converts the original energy-based model training from the log likelihood maximum log likelihood to a conditional modeling, to a conditional uh, likelihood. This is the px, then this is the conditional uh, px prime given x, or px given x prime. So this they have a lot of content to talk about the mathemat to talk about the math insights. But the basic idea is these two. One is the motivation, another one is the method. So we can check the training. So first with the sample T as the milestone, sample for example with sample one, then use this one. It can use the diffusion method, diffusion models method to get a pair. Then we start from the YT as the XT plus one. Start from here XT plus one and use the SGLD to update it. Finally, we get a final YT. Then use the energy-based model, the the loss to train the energy-based model. This is the basic idea. This sampling code we will talk in the I will talk about it in the detail part in later. Okay, background. This the energy-based model, more energy-based model EBMs. It defines the density function as this one, then it can write the updating, how to optimize it. It can write be written in these two terms. The second one is the sample from the raw data, distribution of data. And the first term, it's the sample from the model distribution. So the target is to also match the model's distribution to the real data's distribution. So how to sample from it? Use the for example, use the Langevin dynamics from some random noise, then following the gradient with some noise to sample. Okay, the shortages. The first one is it requires k steps every iteration, so it's slow and unstable. And the second, not no valid steady states. So it will cause some oversaturated samples. You can see here maybe the best one. Here this two may be the best one. However, if you keep sampling, keep keep the gradient descent, it will have some unrealistic images. And third one, it cannot give the accurate density estimation. You can see the toy example. From the raw data, it can generate good samples. However, the density estimation is not accurate. But this I don't know why. I'm not really get the idea of this problem. So how to improve or solve those issues? In their paper, it's really a complex paper, I think. Yeah, a bit. Yeah, it's a complex paper. But I think uh, the authors proposed the idea in another way, not following the structure of the paper. The paper will write in another. Yeah, they organize their paper in another way. But I think they proposed the idea is in a different uh, fashion. So basically, I think they first noticed that currently the GAN and the diffusion or score matching model are the state of art models. But GAN it's uh, yeah people have tried it with energy-based model, uh, so it's not a very good problem. It's not easy. They didn't consider this one. But the diffusion model, uh, nobody tried it. Nobody tried to combine the diffusion model with the energy-based model yet. Nobody have tried it yet. So the motivation is, yeah, the very simple motivation is you can combine the motivation, diffusion denoid model with the energy based model because the this one is the state of art. They have the best generative quality. So then they apply some their awesome math skills to create the math modeling content. Yeah, they firstly introduced this part. So now we have the motivation. We want to combine the diffusion model with the energy-based model. Then, what is the diffusion model? Yeah, it's from some physical phenomenon, like a drop of ink. Yeah, we drop a drop of ink will diffuse in the water, in water. Maybe know this one in water. So they use it. They model this diffusion process in math. So each step can be viewed as adding a Gaussian noise, uh, adding the Gaussian noise to previous step. We don't need to learn this 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 diffusion process. So we can see this example from X0, a raw image. We keep adding more and more Gaussian noise. Finally, it will become a totally random images. So for each step from xt minus 1 to xt, it's uh, we don't need to learn any parameters in this step. So it can get the status. Uh, it can get the status of the time step from time step 0 to the capital T. And of course, every step t minus plus 1, t, and t minus 1. Then what to learn? What it should learn? It will learn the reverse process with the theta. So it's the p theta t given t to t minus 1, the reverse process. So now we know this is the basic idea of diffusion model. Then how to apply it uh, on the energy-based model or SGLD? That's a question. So we know SGLD is samples from in if we use the diffusion annotation T and the 0 uh, in this way one. So SGLD it will samples from T to 0. But the problem is that it will just follow the gradient without any indicator or stop sign, without any flags here to say, okay, you stop here, you finish your sampling. No such indicator. So that's the problem. Then we can easily to combine this. So obviously we can combine this diffusion model using those status to energy-based model. So it's so we can have different status, di different status, different stop sign, or different uh, yeah middle middle steps, intermediate uh, target targets to let the SGLD to go to that to move to that place. Yeah. Okay, so this milestones. Now we have several milestones. So given the status of t minus 1 or and t or t and t plus 1, never mind. SGLD we use S they use not me they use SGLD to learn how to do the reverse process from t to t minus 1. Okay, so the idea is really simple. Then uh, they adopt the definition or they adopt the formula from the diffusion model DDPM from that paper. The diffusion model will follow this conditional Gaussian distribution in every step. So from x0, from then update it with this coefficient, and this coefficient times the epsilon times this one is the Gaussian noise with this sigma coefficient to update the xt to xt plus 1. Then to simplification, they define the yt equal to this times xt. Then they don't need to write this complex definition. Okay, so this is the diffusion model. This is the formula from diffusion model. Then to learn the reverse process of every time step, we can see t to t minus 1 is a time step. We will use one energy-based model to represent it, to learn it. So we will have a sequence of energy-based model, t or t minus 1 energy-based models. We have several energy-based models to learn the xt to xt minus 1. Okay. So yeah, maybe I repeat this part. An energy-based model originally, it just models the density function of p of x. But now we will model another one. We will model this one, right? We will model this x given x t plus 1, no, t, x t. Yeah, we will model this density. Oh, because we have known this one. Then how to write it, how to give the formula. Maybe you can stop for a while to try by yourself, because if you check it carefully, you can clearly notice for this conditional probability, you obviously you can use the Bayesian rules. So it's very easy to get the idea. Then you can do it. It's not hard. You, this one to rewrite in the Bayesian rules, then you can get the definition. Yeah. To simplify it, I give those definition and change the annotation. I don't want to write too much t and t plus 1, t minus 1. So how to write it? It's a Gaussian. Use the Bayesian rule. So give yeah. Let me see. So I don't want to write it here. I just show the, because no, if you know no if I since I know the Bayesian rule, so it's very straightforward to get the idea. So we can see it's this one is px, the joint distribution divided by this one, and this one can be rewritten in this as the production of these two this distribution. Then we follow the definition of this p theta of x. It's this one, and this one, because it follows a Gaussian distribution. So yeah, we get this definition. Finally, so since this and this epsilon, no, not epsilon. Let me see. Epsilon. Oh, okay. Exponential. Yeah, exponential. So these two can combine together to get this one. And write it in energy one. It should be a negative energy. So energy will be negative F plus yeah. Okay, so this is the definition in the 3.1 section. In the paper they first talk about it. Okay, so in this paper, previously we write it as x and x prime, but from previous slide, we know we want to model the xt plus 1 to yt, because here yt equal to this one. We use it to represent, we use it, then we just want to learn the epsilon here. We want to learn the epsilon here. And so we can follow this definition to get the energy function. This one is simple, just the constraint, the distance constraint on the x to xt plus 1 to the yt. And this one, basically we have this yt as the input, and also the t, the time step, as another input, because we want to train several energy-based model. We want to train a sequence of energy-based models, so we use this t to represent the conditional. It's a conditional model. Use it as a time step embedding, but maybe you can check their code. Then based on this formula, we can rewrite this SGLD. Okay, so this is the diffusion, the basic idea. Then the algorithm is simple, as shown as previously, shown before. We sample a time step t from the 0 to t minus 1, get the time step, then use the diffusion process to directly get the yt and the xt plus 1. Then we start from the xt plus 1, then use the SGLD to update it to get the yt minus 1 as the uh, generate images. We generate the we sample from the model distribution, then we update it. Use this one as the raw image, this one from the SGLD again as the fake images, sampled images from the model distribution to update it following following the standard energy-based model training. This is the training part. And sampling part, the progressive sampling, we start from the x capital T from a Gaussian noise. Then for a loop from t minus 1 to 0, I think, or from t minus 1 to 1. First, we get this xt, we get the xt plus 1 as the starting point. Then use this SGLD to update because use it as yt to update it. Finally, we get a new yt, and following the definition of the yt, the relation, the yt equal to this xt to get the new it and keep training. Use the loop to keep training. Finally, from t to 1, finally we get x0. So this is a progressive sampling after training. So we train a model, then use the model to do this sampling. So this is the pseudocode of their algorithm. So results, we can see their methods can improve a lot from previous energy-based model, because for those energy-based model, they only use one model, use one model. But the inception score is a bit low, right? The FID is much better than those energy-based model methods. And compare with the score base. This is the diffusion model, also the score based model, and the GAN is much close. But the inception score is a bit lower. FID, yeah, FID is also a bit low, but improve a lot from the previous energy-based model. This is the results. I talked too much about it, and yeah, we know that as we know, the author said the energy-based model training it takes a long time, right? Because it requires SGLD to train it. Uh, it's very slow. However, this method is even slower, much slower than original energy-based model training. Uh, yeah, for example, the previous one, this one, or this one, they just use k equal to 40 is enough. Yeah, it's really enough to train it. Then if for their method, they compare with the k equal to 180 to get the FID, which means this method original energy-based model training will have something like the bond. The method cannot generate really much better images. And this diffusion model. For their method, we can see they try t equal to 6 and k equal to 10. Then they cannot train anything. Maybe it's not stable again. And for k equal to 30, yeah, they can get this one. But it's much slower because first compare with the previous IGBM or GEM, they just required like 20, 40, k equal to 20 or 40. Now it's 30 is just comparable, not a really no improvement, no acceleration in speed. And another problem is that they train with much more iterations. So finally, the authors will use 8 TPUs and train 40 hours on Sivaton dataset. Yeah, that's really a long time, right? Because for Gem, if you train Gem, maybe like take 4 days, 4 or 5 days in one GPU. Then this 40 times 8, 312, more about 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 15 days, I think. So it's much slower than Gem, because it's very hard to converge. It's improve very slow. For Gem, maybe you don't need to train, even don't need to train 4 or 5 days if you only consider the image quality. Maybe 2 days is enough to get the bounce, to get the best performance. Okay. Okay, to be continued because it's have a lot of math. That session I cannot cover in this time. Yeah, it's really hard for me. Okay, thank you.